Yes.
Okay, great, thanks. So I'm Xuejiao, and today I'm going to present the distributional robust bidding strategy for wind storage aggregator. And this is a joint work with Professor Gabriela Hug, Power System Lab, ETH Zurich. So I first describe the problem we're trying to solve here, and then I will start with the deterministic formulation of the problem and show you some related results, and I'll move on to the stochastic formulation and show some results. And finally, I will give you the conclusion. So the renewable energy market is expected to experience continuous worldwide growth and to compete with conventional units and to deal with the fluctuations and uncertainty of the generation outputs of the variable generation units. It's often combined with the with other resources, for example, the storage units. So in this work, we focus on an aggregator like this one that participates in both the day-ahead energy market and the balancing market. So the aggregator will be acting as a price maker in the day-ahead market, and all the imbalances caused by the forecast errors will be cleared in the balancing market. So the questions we're trying to answer here are as follows. So first, what is the aggregator's optimal bidding strategy and how does it impact the market? Secondly, how can the effects brought by wind forecast uncertainties be mitigated? And finally, what is the benefit of combining wind with storage units? So I will start with the deterministic formulation without considering any uncertainties. So as I've mentioned, the aggregator bids into the market considering its market power. So here we use the bilevel model structure to model this kind of behavior. So in the upper level, it's a profit maximization problem, and in the lower level, it's a market clearing problem. And in the upper level, the objective we're trying to the objective is that we're trying to maximize the profits of the aggregator from both the day-ahead market and also the balancing market. And the constraints we consider here are the offering and bidding quantity limit constraints, the wind output limit, the operational constraints of the storage units, and also the power balance constraint of the aggregator. Notice that the delta T here represents the forecast error of the wind outputs, and in the deterministic formulation, this is set to be 0. And the lower level, the objective is to minimize the social losses, the total social losses. And the constraint we considered are first the dispatched offering and bidding quantity limit of both the aggregator and the other market participants. And other market participants are assumed to be non-strategic, meaning that their bidding offering quantity and bidding offering price are assumed to be fixed parameters. And finally, the dispatched market supply should be balanced with the dispatched market demand. So before showing you some results of the deterministic formulation part, I would like to quickly walk you through the case study setup. So table 1 show the wind storage aggregators parameters we use for the simulation, and for the electricity market data and wind forecast and output data, we use the ones from Denmark region, not pool system, and the simulation horizon is 1 year. So let's first see what are the effects of the market power. To answer this question, we run the simulation for 2 different cases. First one is a price taker case where we assume the aggregator bids all forecast output at a price of 0. And the second one is a price maker case while the aggregator basically optimize both the bidding quantity and the price to maximize the profits it can make from the market. So the results shown here are the first yearly social welfare and the demand, the average demand met in the system, and also the average market price in the day-ahead market, the yearly day-ahead profits the aggregators make, and also the market share of the aggregator and the curtailment of the wind generator. So it can be seen that actually compared to the price taker case, the price maker case makes more profits by curtailing the wind, and by curtailing wind, it can achieve higher prices in the day-ahead market. However, if we look at the demand coverage rate, we can see that there is limited space for exerting the market power because the demand coverage rate in both cases are already quite high. So we've seen that the price maker, like the aggregator, can exert the market power by using this curtailment of the wind. But we know that in a lot of countries, we have this kind of like output-based subsidies. And actually the subsidies will only be paid if the generator actually provides output. So so what will the aggregator behave in if there are output-based subsidies? So here I show two results for the case with subsidies and without subsidies. So you can see that actually the aggregator needs to balance to make a trade-off between obtaining the profits from the day-ahead market and also obtaining the subsidies from the government. So compared to the case without subsidies, for the case with subsidies, there is less wind curtailment because like the aggregator tries to curtail less wind and increase the subsidies from the government. And in this case, the day-ahead market price is decreased in this case. And if we look at the social welfare, we see a increase in the case with subsidies. However, if we compare this kind of social welfare increase to the subsidies paid to the aggregator, this is really negligible. So now let's move on to the stochastic formulation part. So in this work, we model the uncertainties using the distributionally robust optimization. And because of the time limits, I will just briefly describe the principles of this method and also the main steps that how we apply this method here. And for the detailed reformulations, you can refer to the paper. So assuming that we imagine that we have a bunch of data, normally it's the historical data, and the idea of the DRO is to first extract the main statistical information from this data set, for example, the expectation, the absolute deviation, the upper and lower bound. And this uncertainty set actually describes a family of possible distributions like this. And what we are trying to do is that to find a solution that are immune against the worst distribution among this. So the steps to apply this method is as follows. First, to extract the statistical information from the data set, and then to build uncertainty set like this one. And since we still have infinite realizations of uncertainty, so to make the problem tractable, actually to make the problem tractable, we approximate the recourse decisions using the linear decision rule. And finally, we incorporate uncertainty set constraints using the duality theory. So as we know that there are like correlation of the forecast errors within different time steps. So in this work, we're trying to use this kind of correlation by applying the autoregressive moving average method. So the idea is that for each time step, for each simulation day D, we apply the AMA method to generate scenarios of forecast errors for day D using all the historical information until day D-1. And then we update the uncertainty set using the scenarios generated by this AMA method. And we do it for in the rolling horizon way. So now let's see what are the effects of the forecast errors. So to investigate the effects of the forecast errors, we here we show the three cases. The first is the beating at day-ahead forecast, which we consider as a benchmark case here. So beating at day-ahead forecast, meaning that we assume the forecast we made at the day-ahead forecast is perfect. So meaning that we don't consider any uncertainties at real time. So, and the other two cases we consider here are the DRO case and the DRO AMA case. Well, in the DRO case, we modeled uncertainties using the monthly statistical information of the historical years. And in the DRO AMA case, we applied the AMA method we just showed to update day-ahead forecast and to build uncertainty set. So as we can see here, both the DRO and DRO AMA improve the total profits of 1 year of the aggregator. And this is because like for both of this method, they account for the forecast errors at real time. So so in this way, they don't overbid into the day-ahead market. So they have less, losses in the balancing market. Yeah. And the figure below shows the comparison of the day-ahead beatings of the day-ahead forecast beating method, first one, and also the day-ahead AMA method, the third one. So the blue bar here shows the wind forecast arrow, while the positive means that we have actually we have more wind at real time than the forecast, and negative means we have less wind than at real time than forecasted. And the red curve here shows the difference between the day-ahead beatings of this method, the first one and the third one. So we can see that in general, the day-ahead AMA beats capture the uncertainty by changing day-ahead beats accordingly with the forecast arrow. What does it mean? That you can see if we have a negative wind forecast arrow here, actually it will decrease the day-ahead beats into the market. And actually, DRO AMA performs especially better when the negative arrow occurs because it's more conservative. However, when there is positive forecast arrow, we see a delay in responding to this forecast arrow. And this is also related to the characteristic of the AMA method we apply here. So now let's try to answer the third question that we presented in the beginning of this presentation. So what is the value of the storage units? How much profit it will bring us if we combine the storage units with the wind storage, wind generation units. So let's first see how can storage units increase profits. So there are mainly two ways to increase the profits using storage units. The first is charging and discharging to alleviate the price suppressing effect caused by wind. And the second is to reduce the imbalances due to forecast errors through real-time operations. So for the second one, we can see in this figure. So as the same as the figure we just showed before in the previous slide. So the blue bar here is still the wind forecast arrow, while the red curve here shows the real-time battery discharge. So while positive means discharging and negative means charging. So we can see that in general, the battery will discharge in during the hours when we have negative forecast arrow and charge in the hours when we have positive forecast arrow, so that it will have less imbalances in the real time. So now let's see how much profit can storage units bring us. So in this table, we present the results of 4 different cases with and without storage units. So the value of the units storage, the value of per kilowatt hour storage is calculated as the yearly difference between the corresponding case with and without storage divided by the capacity of the storage unit. And the maximum acceptable investment is calculated using the annuity formula here, and the discount factor of 5% and the lifetime of 15 years are assumed. So it can be seen that compared to the first case, where we assume we have perfect forecast, meaning that we know what will happen and we have all the information of both the day ahead and also the real time. And then in this, so these 3 cases actually achieve almost a triple the value of the unit storage. And this is because this is because of the second bullet point we show here, like the storage units increase profits by reducing the imbalances due to the forecast errors at real time. However, we can see that the maximum acceptable investment cost is still around 100 euros per kilowatt hour, which is far below the current market price of the 1 hour utility size storage units, which is around $600 per kilowatt hour at the moment. And but one thing I need to point out is that by looking at these numbers, this number can be changed if we have different market assumptions, and if we consider, for example, reserve market, and also if we consider subsidies for the storage units, and also a lot of things could affect this value. So to conclude, first, compared to the price taker strategy, the price maker strategy can achieve higher profits as it considers the potential impacts on the market. And the numerical results presented also suggest that output-based subsidies might reduce the aggregators' motivation to exert market power. However, when we compare the social welfare increase to the subsidies paid by the government, it's quite a small number. And also the acceptable maximum investment cost of storage based on the simulation results requires a significant decrease of the current price. And finally, the proposed compared to the benchmark, where we showed like the aggregator beats into the market using the day-ahead forecast, but the proposed DRO method and also the DROI method can achieve higher revenues. That's all. So thanks for your attention. And now I'm willing to take any questions if there are.
Great, thank you so much, Xuejiao. You have one question so far in the Q&A. It's how is the imbalance market modeled?
Yep, let me check.
And now there's two more.
I think okay, yeah. So the first one, I'll first read out the questions. So first is how the imbalance market modeled. So basically the imbalance market price we take from the not pool system, as I just mentioned. And however, in the not pool system, they have the dual pricing system. So basically for each hour, we just take the one that is different from the day-ahead market price. However, since we model a price maker in this method, so we have this price suppression effect from the aggregator. So basically, we use equation in the simulation we made to modify the imbalance price to make sure that for the positive imbalances, the aggregator will get less than the day-ahead market, and for the negative one, it will be penalized. Yeah. And for the second question, the second question is the battery only used to balance wind power output arrow, or it is used in the bidding optimization problem? So the battery is, quick answer is that the battery is used for both the day-ahead and real time, if I understand this question clearly. So so as presented in the on the slides, so one way the battery can increase the profit is to make the arbitrage between the different prices between hours, and the other way is to to reduce the imbalances at real time. Yeah.
Great. And you just have 1 more minute, so if you could answer the last one.
Okay, so the last one. Thank you for a great presentation. I may have missed this, but what does your distribution of the forecast arrow look like? And how can you clarify why perfect forecast has lower profits compared with accounting for forecast arrows, which triples profits? For the second one, I think the perfect forecast case has the highest profit. Maybe it's a misunderstanding or something. And for the first question, how do I model the forecast arrow? Basically, the benefit of using the distribution and robust optimization is that we don't need to assume any specific distribution of the forecast arrow, but we use the uncertainty set to describe like a family of possible distributions. So using some partial statistical information to describe this. Yeah.
Great.
Yeah.
Thank you.